All right, here we are in lecture B, and I was reminded that I forgot to do the infinitesimal approach with the center of mass in the y direction. Essentially, in a nutshell, all the d's, all the deltas, the capital deltas would get replaced by d's. Be thought of as infinitesimally small quantities. They're smaller than any standard positive real number. And the summations, well, the approximately equal to's would become equal to's, and the summations would become integrals, effectively. That, in a nutshell, is the difference in the approaches. The differential infinitesimal approach does get you the answer more quickly. But for sake of time, I'm not going to actually do that. At least not today. We're going to talk now about the work done by a force. Certainly we'll get to springs and Hooke's laws, and I'm hoping I can do chain hauling as well. I think I will try. I'd like to finish in 15 minutes here. Work done by a force, okay? I've got a book here. What's its mass? I don't know, pretend it's 2 kilograms. If I hold that book steady, I am applying an upward force against the force of gravity equal to the force of gravity on the book, which is 2 kilograms times 9.8 meters per second squared. M times g. G is the acceleration due to gravity. Turns out that would be 19.6 newtons would be the weight of this book in standard units, and that is the same as the force I'm applying. If I move it upward at a constant velocity, it's still the same force. The mass, 2 kilograms, which is what I'm pretending it is, times the acceleration due to gravity again. The force I'm applying at a constant velocity is a constant 19.6 newtons. The work done by my force, if the object moves, is just that force times the distance that you move it. The work done by a force in the direction of motion is the force times the distance. In this case, 2 kilograms times 9.8 meters per second squared. That is the force. So times here. And I could move it 1 meter. Let's pick something different than 1. What if I move it 0.5 meters? Okay. I'll go ahead and keep it at 0.5 meters. This ends up being 19.6 newtons times 0.5 meters. 9.8 Newton meters. Newtons times meters for the units. This unit has a special name. It's called joules. And you use the letter J for it. Hopefully you know, maybe you don't, that joules is also a unit of energy. The units of work are the same as units of energy. In fact, the work done by the force is related to energy. For example, when I do move the book up by half a meter, the work done would be 9.8 joules, and that would be equal to the change in potential energy of the book, for example. Okay, if I move it up by half a meter, if the book really is 2 kilograms, the change in potential energy would also be 9.8 joules. So work is definitely related to energy. You should know, though, that if I hold a book steady and walk horizontally, my upward pointing force is doing no work. This equation only applies to forces that are in the same direction as the motion. Of course, I might be getting tired still, and I guess I'm still doing work on my body plus the book in that direction, but the upward pointing force itself is doing no work. Things get more complicated if we consider situations where the force might depend on your location. One such a situation is a mass on a spring. Imagine a wall over here and the floor down here, and you've got a spring attached to the wall. Spring could have a mass on it. I'm not going to really be thinking about the mass so much. I'm going to be, here initially at least, just thinking about compressing the spring. Say the location of the mass, or at least where I push the spring. Maybe I should just put a line here as the spot where I put my hand to compress the spring. I'm going to say the position of that line is position 0. And I'm going to imagine compressing the spring by a length x. To the left, so effectively here, by making my drawing the way it is, I've taken the positive x-axis to be to the left. That's okay. I can do that. I hope it makes intuitive sense to you that if you push a spring, if you compress it from its equilibrium position, which would be at 0, that you're going to have to apply a stronger and stronger force to keep moving it at a constant velocity, because the restoring force of the spring keeps increasing in its strength. In fact, something called Hooke's law says that the strength of that restoring force is proportional to the value of x. Is that really true? According to experiments, it's at least approximately true for small values of x. Now, x can't be too big because otherwise you break the spring. You can't push it past the wall, for example. But for relatively small values of x, evidently experimentally this works pretty well. It probably is more of an empirical law. It's an approximation, a nice approximation to the truth. The value of k is called the spring constant. You could think of it as f divided by x, and you could find its value evidently by applying a known force and seeing how far you can push it, I guess. And its units would be newtons per meter, because it's a force divided by a length. If you don't know what a newton is, okay, you may not. I didn't think about that when I first mentioned it. It is a unit of force. It's the standard SI unit of force. And based on what we did before, it's the same as units of kilograms mass times units of acceleration, grams per square, meters per second squared. But if that doesn't make sense to you, you don't have to worry about it. It's just the standard units for force. Let's pretend we know the value of k. In class, I picked a value of 0.2 newtons per meter. That ended up being pretty small. I think I'm going to pick a different value here for the sake of this video. Let me pick, say, 3 newtons per meter as the spring constant for a particular spring. Okay? Springs are stiff when k is large. Think of a real thick spring that would be hard to push. When k is small, that's not a stiff spring. That's maybe more like a slinky. All right? Question here is, what is the work done to move the spring from equilibrium to, say, 0.2 meters? Or compression of 0.2 meters is maybe a better way to say that instead of move. Maybe to compress the spring by 2.2 meters. Eq here means equilibrium. And what you want to do is you want to imagine thinking about moving the spring a small amount. Say you're at an arbitrary location, x, and you move it by a small amount, delta x, from x to x plus delta x. So along an axis that's positive to the left here, this would be position x plus delta x here. That work, which you might call delta w, is not equal to, technically speaking, the force at position x times delta x, but it would be approximately equal to that if delta x is small. Force times delta x, where the force is the force you're going to apply at position x, k times x. Which for us, k is going to be 3. When you look at this expression, you're thinking of x as fixed, and you are moving it by delta x. Technically, this is an approximation, because technically, even for a small compression, the force needs to keep increasing. But if it's a small enough compression, this should be a good approximation. The total work then would be the sum of these delta w's, which would be approximately the sum of these quantities, And then you say, hey, that looks like a Riemann sum for the function 3x over the interval from 0 to 0.2. And so to find the work done, you let delta x go to 0. In the limit, you get an integral from 0 to 0.2 of 3x. And that would be your work done. This would equal 3 halves x squared, going from 0 to 0.2. 3 halves times 0.2 squared would be 1.5 times 0.04, and that would be 0.06 joules for the work done. Zoom in if that's too small to see from far out. That would be the answer to the question. Yeah, I think I do want to try to get in a basic chain hauling problem here. And give you a problem or two that is similar from the book for the next homework assignment. Imagine you're standing on the top of a building and you've got a chain that you're holding on to that's hanging down the side of the building. Maybe it'd be better to think of this as a rope. And you've also got, well, okay, maybe it's better if you're thinking of yourself as lying on your stomach here as you haul up this chain. So effectively the height of the building is the total height to haul the chain. Maybe the building is 50 meters tall. And the chain goes all the way down to the bottom, like that. You want to haul the whole chain up, and you're wondering how much work do you have to do to haul the whole chain up? Drawing the whole chain there. It's good to imagine a coordinate system, perhaps with the positive direction downward. Call this the plus y direction. And think about how much work is necessary to haul a small chunk of this chain up a certain distance, y. The small chunk being of height delta y. Then add up the total work for each of those small chunks to find the total chunk, the total work, approximately, and then in the limit as delta y goes to 0, you get an integral that you can do to find the total work. You are going to need to know something, though. You are going to need to know the mass density of this chain, the linear mass density. Think of it as a one-dimensional object, which is why a rope might be better. But let's say we've got a mass density of, and it would make sense to use a constant mass density, actually. I don't know, maybe 2 kilograms per meter. Might be the mass density. It's a constant here for the chain. The thing that changes here, that requires an integral in this case, is there's not a varying density here. It's the y distance that changes. Okay? So that's the thing that ultimately requires an integral. Different chunks travel different vertical distances. The small amount of weight to each chunk is really a small amount of force. Delta F is the small amount of weight of each chunk here, which would be the mass density, kilograms per meter, times the length of that small chunk. This would be actually, I guess, an exact equation, 2 times delta y. And this is going to be in, oops, let's see, oh, I forgot my acceleration due to gravity. That's going to be the mass of the chunk times g, the acceleration due to gravity, 9.8 meters per second squared. Giving you the product will give you the force in newtons, which if you plug in 9.8 there is going to be 19.6 delta y newtons. That is the weight of the small chunk. You can think of that weight as being a force. For hauling that particular chunk up, you've got to apply that force to that chunk. Of course, you're applying more because there's there's the entire chain. But focusing just on that chunk, that's the force you have to apply to counteract gravity. The work then for the small chunk, which you might call delta W, this would be an approximation. It would be delta F times Y, and it's an approximation because Y is technically not the same for every little piece of the small chunk. The total work then is going to be approximately the sum of these things. Delta F again is 19.6 times delta Y. And rewriting this a little bit allows you to see that it looks like a Riemann sum for this function, 19.6 times Y, over the interval that Y varies over. Y varies from 0 down to 50. The height of the building is 50. So the total work is exactly going to be an integral. You let delta Y go to 0. Integral from 0 to 50 of the function 19.6y. That will give you 9.8y squared, evaluated from 0 to 50. 50 squared is 2,500, so we get 9.8 times 2,500. I don't feel like doing that in my head, and I'd like to end the class here. Whatever that ends up being in joules, that would be the answer for the work done in hauling this chain up. And then I think I'll end the lecture right there.